Photochemical reaction centers are complex structures that drive photosynthetic processes. Evidence of the existence of these centers were provided as early as 1952 when Louis Duchesne discovered that when he pulsed a light with a wavelength of 870 nanometers to photosynthetic membranes of purple bacteria, it caused a temporary decrease in absorption of light, aka bleaching. Thus, Bessel-Koch and Worstheidt also discovered this using 680 and 700. Very clever. The first photochemical reaction center we're going to go over is that of purple bacteria. The photosynthetic machinery in purple bacteria consists of 3 units: a single P870 reaction center, a cytochrome BC1 electron transferrin complex similar to that of complex 3 in mitochondria, and ATP synthase, also similar to mitochondria. Illumination drives electrons through pheophytin and a quinone to the cytochrome BC1 complex. After passing through the complex, electrons flow through the cytochrome C2 back to the reaction center, restoring its pre-illumination state. This light-driven cyclic flow of electrons provides the energy for proton pumping by the cytochrome BC1 complex. The next reaction center is that of green sulfur bacteria, and it involves the same 3 units as purple bacteria, but the process is different and consists of additional enzymatic reactions. Like usual, excitation causes an electron to move from the reaction center to the cytochrome BC1 complex via a quinone carrier. Electron transfer through this complex powers proton transport and creates proton motive force used for ATP synthesis. Again, just like purple bacteria. Here's where things get different. The flow of electrons in purple bacteria is cyclic. In the case of green sulfur bacteria, some electrons flow from the reaction center to an iron sulfur protein ferredoxin, which then passes electrons to NAD reductase ferredoxin, producing NADH. The electrons taken from the reaction center to reduce NAD+ are replaced by the oxidation of hydrogen sulfide to elemental sulfur and then to sulfate. Oxidation of hydrogen sulfide is chemically analogous to the oxidation of water by oxygenic plants. Photosystem II is a phytophytin quinone type of system, just like purple bacteria. It is dimeric, and each monomer is a huge complex of 19 proteins, including the core complex of the P680 reaction centers, and proteins D1 and D2, the chlorophyll binding proteins CP43 and 47. It also has carotenoids, a non-heme iron, and an inorganic complex. 16 of the proteins have a transmembrane segments, but 3 are peripheral proteins on the P side that stabilize that complex. When a photon is absorbed by any of the antenna molecules, the resulting excitation moves very rapidly until it reaches D1 and D2. Excitation of the P680 reduces P680, which transfers that electron to pheophytin, giving it a negative charge. With the loss of its electron, P680 is transformed into a radical cation. Pheo, the extra electron, is going to be donated to plastoquinone A, PQA, which turn passes another electron to plastoquinone B, PQB, or QB. When PQB has acquired 2 electrons and 2 such transfers from PQA and protons from solvent water, it is fully reduced quinol form, PQPH2. Photosystem I is related to type 1 reaction center of green sulfur bacteria. It has a P700 reaction center and a high ratio of chlorophyll A to chlorophyll B. Photosystem I is a systemeric trimer. It consists of core chlorophyll molecules, light harvesting complexes, chlorophylls that span the gap between the complexes and the reaction center, and it also contains lipids and carotenoids. When P700 is excited by a photon or exciton, this results in charge separation of the photochemical reaction center. P700 plus is a strong oxidizing reagent which quickly acquires an electron from plastocyanin, a soluble copper-containing electron transfer protein. AO passes the electron through the train of carriers that leads to NAD+. Phyloquinine accepts the electron and passes it to an iron-sulfur protein through the 3 iron sulfur centers in photosystem 1. From here, the electron moves to ferredoxin. Two things can happen: this cyclic and non-cyclic process. In the non-cyclic process, a fourth electron carrier chain, flavoprotein ferredoxin, NAD plus oxoreductase, transfers electrons from reduced ferredoxin to NADP+. The B6F complex connects the two photosystems. Electrons temporarily stored in plastoquinol as a result of excitation of P680 are carried to the P700 via cytochrome B6F complex and the soluble protein plastocyanin. The cytochrome B6F complex contains a B-type cytochrome with two heme groups, BH and BL, a RISC iron sulfur protein, and cytochrome F electrons flow through the cytochrome B6F complex from PQBH2 to cytochrome F, then to plastocyanin, and then finally to P700+, thereby reducing it. Reaction centers have very great evolutionary advantages, one being that the proteins are so closely aligned and in the right position that it combats high efficiency and rapidity of the reactions, leaving nothing to random. The electron transfer reactions are not only fast, but they are thermodynamically downhill. This makes it have a negative and large standard free energy. The best part is it prevents internal conversion, which would typically just create things to heat. This is the end of the presentation. Thanks for watching.